All right, so today the first thing we'll do, we'll go over the quiz 2, the results of quiz 2, or the answers rather, and then there's a mistake that I made in the third exercise for lab 7. I want to finish that and show you what the mistake is, and then we'll just move forward with where we left off last time. So let's take a look here at quiz 1. And the first problem was to draw the UML class diagram for the bean jar class. Let's take a look at that. Let's see, I think I may have an example of that here somewhere. Which lab had the UML diagram in? Does anyone remember? This one right here. There we go. All right, this is the, there we go. There's 3 sections in a UML class diagram, 3 boxes, and the top section gets the class name, and the second section gets the variables, the member variables. The third section gets the member functions. And as you can see, there's a constructor here. So let's replace the that other constructor with this one. Is there a print function? Let me look here. Oh, here's the constructor. By the way, the constructor here takes 2 arguments: max number of beans and initial number of beans. So that should be listed in here. We have max number of beans, and that's an int. And then we have initial number of beans, and that is also an int. And we're kind of running out of space there. Let's see. Let's bring that over here. So we're going to need to move everything over. I mean, I'm gonna we'll do that. Maybe finish that in a second. That's so we have. Let's go down and look here. So we have the. We just basically we go through the declaration of the class and put the information in this diagram, right? The first piece of information is the class name that goes in the top section, and then in this section here, which is listed as public, right? That we want to put the plus sign in front of everything that's in the public section, and in the private section we'll put a minus sign, right? So that means it's not. Those are functions and variables that are not visible outside of the class. Those are private. But the functions and variables that are accessible outside of the class, those are public. So the bean jar constructor is public. So we have a plus sign here. Let's look at what else we have there. We have AddBeans, and that's public, and it returns a bool. Let's take a look at that. That's public. It's called AddBeans, and it takes number of beans to add, and that's an int. So we put the data. We give in the UML class diagram format. We list the name first, and followed by a colon, followed by the data type. It's the same with the function. The function also, the return type comes after a colon at the end of the function declaration. All right, let's look at the next one. RemoveBeans, number of beans to remove. So this will be GetNumber of Beans returns an int. That's also public. GetNumber of beans. It takes no arguments, and it returns an int. Is anything else in there? That's it. So those are the public members, and these are all functions. So at this point, this is finished, and there is no print, so take that out. Just clean this up a little. Now this section here, the second section, holds the member variables, and we'll get those. Those appear here in the private section of the class declaration. Max number of beans and number of beans. Max number of beans is of type int. And what was the other one? Number of beans. That's an int as well. So that's the class diagram. Let me clean it up a little. Any questions on the class diagram? Okay. Now we have the second problem. Implement the AddBeans function. Excuse me. So to implement this correctly, we have to make sure that we read the comment in the class that explains how this works. The class provides functions to add beans, remove beans, and get the number of beans that are currently in the bean jar. So instances of this bean jar class represent jars that hold beans, right? And in a given jar, the characteristic that we're interested in is how many beans can it hold, and how many beans does it have in there. And the other thing that we want to sort of represent abstractly in software is the ability to add additional beans to the jar and take beans out. So the functions to add and remove beans return a Boolean value that indicates whether the operation succeeded or failed. So we're going to return false to let the calling code know that what it's trying to do was not accepted. And we return true to say everything went fine. When one of these functions fails, the number of beans in the jar will not have been changed. So if the capacity of the jar is 10 beans, and someone tells us to add 100 beans, maybe there's 1 bean in the 10 bean jar, and someone says to add 100 beans, but we don't do anything. We leave the number of beans in there at 1, and we return false. So there's an example in the comment there. So let's add the beans. So what we're concerned here with is for adding too many beans. So if we're adding too many beans, if we're asking for too much, then we're going to return false, so do nothing. Else, we're going to change the number of beans that are in the jar. And we can do that with this plus equals operation. So if we're asking for too much, we're going to return false. Otherwise, we're going to go ahead and add those number of beans. I have to do a little more there. We have to return true, right? So everything went according to plan. All right. So the hard part here is, what is it? How do you make an expression that evaluates the true or false that that captures this concept of asking for too much? So if number of beans to add is too big, then return true. So we want an expression that is true when the number of beans to add is too big. So if the number of beans to add is too big, let's say it's you know, a big number. If we're asking for too much, then we're going to return false. You see what I'm doing? I'm just getting there one step at a time. I'm not getting the whole concept all at once here. I'm just trying to work my way to the answer. All right. So what does that mean? So if the number, what number is well, we have the max number of beans that the jar can hold, right? Well, clearly, if we're trying to pass in a number of beans that exceed the capacity, then that's too many. But what happens if the bean jar has beans in it already? Then that, in a sense, it reduces the unused capacity. So we want to compare number of beans to add with the unused capacity. The unused capacity is capacity, or the max number of beans, minus the number of beans that are currently in the jar. So if the max number of beans is 10, and we currently have 5 beans, it means we could fit 5 more beans. So 10 minus 5 would be 5, right? So we have a capacity of 5 more beans. We can fit 5 more beans. So if you tell me to add 5 beans, I'm okay. So if you pass in 5, this expression is false, because 5 is not bigger than 5. 5 is good. So that means we add in the 5, and then we hit 10, and we return true. But if you pass in a 6, well, 6 is bigger than 5. And so we return false and don't do anything. You see how I went one step at a time to the solution? I didn't like visualize the detailed solution, you know, in the beginning. I just sort of crafted it, you know, one step at a time. And then when I got to the end, what did I do? I checked my work. I used a specific example. I said, well, let's suppose we have 10 beans in the jar, a capacity of 10 beans, and then if there's 5, you see that process. That's the process that, you know, I'm illustrating to you. Maybe there's other ways of solving these kind of problems. There probably are, you know, and you can develop a process that works for you. And I'm just showing you the process that works for me. And I do think it's probably the common process. All right, let's do the RemoveBeans is already implemented. Let's look at the third problem, which is to add the test code to test the RemoveBeans function. make sure the test code executes all lines of code in the RemoveBeans function. So you can see here. So in other words, we want test code that causes this function to return false, and also causes the function to return true. So we need at least two kind of actions. We're going to call RemoveBeans at least twice in order to execute every line of code in the function. All right, let's see. So here we have our bean jar instance. So in the first line, we're creating an instance of the bean jar class. So we have the class name here. That's the uppercase B, see? And by convention, class names their names start with an uppercase character. And then the variable name starts with a lowercase character. So it's easy when you're reading the code and you get down to here and you see bean jar with a lowercase b, it's easy to quickly say, oh, that's an instance of bean jar class, uppercase B, bean jar class. That's the reason to make these names so similar. So that as you're later on in the code and you're looking at the variable name, the name itself gives a hint of the name of the class. So you know what you're doing. Now the constructor takes two arguments. The first argument is the max number of beans that can be stored in the jar, and the second argument is how many beans are currently in the jar. So here we're creating a bean jar that can hold 10 beans, and it has 5 beans initially. So we'll test. So we use this assertion here in our bean jar class. We call GetNumber of Beans that returns number of beans, and we test that it in fact equals 5. And then when we call AddBeans with 3, now the bean jar should have 8, because 8 is less than the capacity, so we're okay there. So we test that with an assertion here. We call GetNumber of Beans should return 8. But now that we have 8 beans in the jar now, and when we try to add 4 beans, it should fail. It should return false, and we test that here. See? So when we call AddBeans, returns true or false. So it returns false when the operation fails. So that's why you have to negate that. So whatever the whole idea that when you look at assertions, whatever you put, the expression that you pass into the assertion needs to evaluate to true. So we're doing something bad. We're trying to add too many beans. It's going to return false. We've got to convert it into true by using that not operator. And the number of beans in the jar should not have changed. So then we test it here. So let's try removing some beans. Let's go ahead. Let's remove 4 beans. So if we had 8, then we should have 4. Oh, and this should succeed, right? But be careful when you're copying code. So remove beans. We should be allowed to remove 4 beans at this point because we have 8 in the jar, and then we're left with 4 beans. Now that was a good removal, right? That means we return true here. So we exercised these 2 lines of code. We exercised this. We executed this condition in the if statement, but we didn't execute this yet. So we haven't fully tested the function yet. We haven't tested it to the degree that I asked for in the exercise, in the problem, rather. So let's do this again. And so we have 4 beans. Let's do it again. Let's just do it the way it is. It should be. This is kind of testing a boundary condition. So we're removing all the beans. We should have 0 beans. Rather than trying to, we'll just test to make sure it handles the 0 case correctly. But you didn't need to do that for the quiz. But at this point, if we try to remove, say, 2 beans when there's no beans in the jar, then this should fail. So we have to negate that. I should return false and convert it into true. Pass it into assert so that that succeeds. And the number of beans should remain the same here, 0. Any questions on this? Okay, now what I'm going to do is show you the alternative implementation for what was it, RemoveBeans or AddBeans? What did I ask for in the quiz? So we need to change the way AddBeans works. That's the first problem, and the second problem is what? Huh?
Change the way we do it for
remove. Both add and remove. We need to modify the way add and remove work. But I didn't ask you to change the test code, so we don't have to do that. But maybe the next time, if I ever use this example again, I'll ask those students to change the test code as well. So here's AddBeans. And here's the... So now, when we add too many beans, we're going to still return false to say that you did something wrong. I can only fit 5 more beans. You passed me 6 beans. I'm going to return false to let you know that something went wrong. But I'm going to do more than just returning false. I'll fill the jar up as much as I can. And so that means I'm going to reach my limit. So I'll set number of beans to max number of beans, and then I'll return false. So it was just this one line. That's all you had to do was show the addition of this one line. Let's look at RemoveBeans. So this is the let's look at RemoveBeans. So it's similar to RemoveBeans, and it's only the false. In the true case, we don't make any changes. We just leave it alone. But if you're telling me to remove more beans than I have, I'm going to return false. And I'm going to do as best as I can to remove beans for you. But so if I have 5 beans and you tell me to remove 6, well, I'll remove the 5 beans and set it down to 0. But then I'll return false to let you know that something is not right. So you just set number of beans to 0 here. And that was it. Any questions on that? Okay. Does that seem easy or not? What's hard is the concept of a class, right? And how you create an instance of it, the constructor, the idea that you have member functions. That's the hard part, isn't it? The logical conditions, that's maybe easier to understand. But how arrange it so that it has this object-oriented structure. I think that's the hard part. Anybody have a question about the quiz? All right, this lab 7 is a problem. We didn't, and after our class, because when we were doing this, I made a mental note that, we didn't finish the problem, but I just went on. I forgot my mental note, but it never disappeared. So I remembered it later on. I think when I was eating lunch or something, it came to me. This is, and I think one of the problems is we didn't fully test this. Let's go back and review what it is that we're trying to do. We're trying to create this. We're working with vectors, all right? So we're solving problems related to vectors, so we understand vectors. And the problem is to implement a function called insert. And what this function does is it takes a vector, and which contains an ordered sequence of integers. And then when we call insert, we pass in another integer, and we want the function to insert that integer in the right place so that we maintain the order. So here, we create this vector v, and we push 3, 6, 7, and 12. Did I lose something there? There we go. So at this point, the vector v looks like this: 3, 6, 7, and 12. And then we insert 8. And at this point, the vector v equals, or should equal, 3, 6, 7, 8, and then 12. That's the right place for 8 to end up. And these assertions here, check that. So v of 0 is 3, v of 1 is 6, 7, 8, and 12. So there's the assertions. And here we clear the vector, we start all over again, and we check the size here. Now it doesn't hurt to put more test code in here. Here the size of v should be 5. And before the insert, the size of v should be 4. So we can go ahead, and the more things we check, the better. So before the insert, we have 4 items. After the insert, we have 5. So down here, we clear the vector. We check that the size is 0. We insert 88. We check that the first slot now has 88. And then we say all tests pass. But we did a poor job here, actually. And it runs, but it shouldn't say all tests passed. Should fail. And let's try to make it fail. And I'm going to show you kind of a subtle thing here. Now the problem is this. Let's look at the algorithm. Here's the algorithm. When we call insert, okay? When we call insert, what we do is we need to insert k into A. So we're going to start by pushing k onto the back of A, and then we're going to compare. And then I, by the way, I is a variable that's the index. That represents the index where k is at. So when we push back k onto the end of the vector, its position in A will be A.size minus 1. That's where k is now. And so A of I is equal to k right now. And A of I minus 1 is the value that used to be at the end of the vector, but now is second to the end. So we're going to compare k with the thing that's before it. And k should, if k is in the right place, then k should be bigger than the thing before it, and this condition will fail, and then we're finished. But if k is smaller than the value that's before it, then we want to swap k with that value. So if k is smaller than the value before it, then we want to move the value before it into where k is now, and then where the value before it was, we want to move k there. And oh, remember, I represents where k is, so we need to decrement I. So we just swapped k with the value before it. And we continue that process until this the condition in the while loop is false. And that's what we want. So while k is in the wrong place, do the swap. And when k is not less than the thing before it, we're done. Let's just stay put. But what happens if let's look at an example. Let's look at this example. What happens if we call what happens if we set v to 3, 6, and then we call insert v comma 1. Then let's look at what happens there. So when we do the insert, you know, at this point, let's do it like this. When we push back 1 onto the vector, we're going to get a vector that looks like this. Should be a comma. 3, 6, and then 1. Okay, so k, which is 1, is in the wrong place. So I'm going to enter into this loop here. Well, sorry, let's keep track of what's going on here. So v is going to equal this, and I is where k is. So I is I 3? No, because we start counting at 0. I is 2. So, and then we enter this loop with v equaling 361 and I equaling 2. So we compare a of I, which is 1, to a of 1, which is 6. So 2 is less than 6. That's the problem. 2 is less than the number that comes before it, and so we need to do the swap. So we take the 6, we take what's in position 1, and we move it into position 2. So when we do this line right here, we're going to write 6 into that slot. That's what happens when we do this right there. So now we have 2 6s in there, and we don't have 1 in there. But in the very next line, we write our 6 into position 1, I minus 1, I is 2. So we write here, we write 6 into, we write 1 into position 1. So that's where it goes. So we swap. You can see now at this point, after you have to execute 2 lines for the swap to become apparent, because for a moment there, when we just execute 1 line, we haven't really swapped. We've just duplicated the 6. But as soon as we get this done, now I is now is no longer accurate as well. We need to decrement I, because remember, I conceptually is the location of k, the value we're putting into the vector. So we decrement I. Now I is 1. That's the position of k. Remember, and k is 1. So we go back. We have to evaluate the loop again, and we compare a of 1, which is 1. Compare that to a of 0, which is 3. So it's true. 1 is less than 3. So we need to do this. So we're going to swap the 1 and the 3, and then decrement the I. Swap the 1 and the 3, and decrement the I. So we just finished this line, and we come back up. We have to evaluate this again. Does anyone see the problem yet? we're going past the front of the array. So now A of 0 is 1. But A of minus 1, wait a minute, A of minus 1? Because I is 0, so 0 minus 1 is minus 1. We're passing in an index of minus 1. So you see the problem, it's undefined. Now, in another language, actually, let's write the test code for this. Let us write the test code for this. So we need to check to see if we're already at the front of the vector, and if we are, that's where the new value goes. So actually, I mean, we're done. See, we're done now. What we didn't we're finished. But the algorithm, the way we implement it, we keep going. But we didn't test this case. See, this is a boundary case. So we're passing in a number that should get into the front of the vector. We didn't test that case, and we should have. We should have tested 3 cases. One case where the value goes on the end of the vector, where the value goes in the middle of the vector somewhere, and then the other case where the value goes into the very front of the vector. So we were not thorough in our tests. Now I'm going to show you something really subtle here. Let's clear V again. And then let's call insert with 3. Actually, that's got to be V, right? V comma 3. And let's insert 6. So at this point, V0 is, actually this is, I don't want to, I guess we can test this insert here. Let's not do that. Let's do this. Let's do pushback, sorry. I want to make sure that's, all right, let's do an operation that we know will succeed. So we know that we can call pushback, and we're assuming that the library is that implements pushback is correct. So we're making that assumption, and then after doing those 2 pushbacks, and we have these assertions should succeed, and then when we push back 3. I'm sorry, not 3. When we push back, well, we insert 1 rather. Then 1 should occupy the first place, and 3 should be in the second, and 6 should be in the third slot. Oh, what is this? Line 4? What did I do here? I clear V and, oh no, these assertions, sorry. Sorry, these are not assertions. And line 69. So insert, we're passing in, is that right? Oh. What's wrong with that? Oh, insert doesn't return a bool. Sorry. I was thinking about the quiz. Okay, insert does not return a bool. There we go. Look at this. All test pass. What's going on there? All test pass. That should fail, right? This should fail, but it doesn't. And let's, instead of pushing back, and let me tell you what I think is happening here. I think what happens is, well, first of all, let me tell you what the vector class, the vector implementation, does not do what's called range checking. So when we pass in an invalid index, the compiler does not generate code to check the index to see if it's valid. -1 is not valid, just uses it. And it does that because the C++ language is built in a way that's, that produces optimal speed. That's the reason why they use it for writing video games. Because if there's ever a situation where there's a trade-off between ease of use and speed, it will go with speed. They'll say, we don't care about the ease of use, speed is more important. But in most other languages, that's not the case. In almost all the other languages, there'll be range checking. So if you pass in a -1 as an index into the vector, that other language will say, hey, that's an invalid index. It will tell you that you have a problem there. But in C++, it doesn't do that. And what's happening here is, I think what's happening is that this, when we do a of -1, it resolves to a memory location that precedes the first element in the vector, and that value happens to be smaller than what we're trying to insert in there. It's smaller than 1. And so we stop. We terminate the loop because we looked at v of -1, but what was in v of -1 was smaller than 1. And so everything was okay. And it looked like all tests passed. But what happens if we pass in, say, a -1? Is the value that precedes the vector that's found in memory going to be less than -1? Well, I'm guessing that we don't know what's in memory, but I'm guessing there's going to be a 0 there. And so that means we're going to try to do a swap. And when we do a swap, we're going to hopefully get something wrong, but maybe it won't. Let's see what happens. Look at that, see? So it says segmentation fault. So segmentation fault means we're trying to address a location in memory that is illegal. So when a program is launched, the operating system gives it a chunk of memory to run in. And if it tries to access memory outside of that chunk, then the operating system intervenes and you get a segmentation fault. So this is a valid test, and now we see that the bug is being revealed. And we have to add the code up here to fix this. So we have to modify this condition. So we have to say, well, this needs to be true, but also, and the following needs to be true. I needs to be bigger than 0. If I were to be less than or equal to 0, I minus 1 would be less than or equal to 0. No, I minus 1 would be less than 0. And an index less than 0 is invalid. So even though this may be true, which was the case when we were trying to test with 1, even though this may be true, this condition is also required. So this means, you know, if I is 0, it means that k is in the first slot. We're done. If I is 0, k is in the first slot. We don't have to look to move it anywhere else. Now we're passing the test. So we had inadequate test code. And so we didn't catch the mistake in our logic because of that. Any questions on that? Okay. What about we're in lab 8 now, is that right? You don't need 100 here. There's no any number you want. You know, 3, 30, anything. So this is a good problem. We worked this out in the lab. And is there, how much time do we have left? It says 1:04 here. We end at 1:15 or 1:10? 1:15, right? Is it really 1:04? Yes. Or is 1:05? Do you want me to try to do this in 10 minutes, or do you want to just call it quits right now? Try to do it in 10 minutes? Ready? Speed coding, 10 minutes? We'll have this done. Okay. All right, web-based class, developed in the earlier. It contains a list of strings. You know what? Does someone have a solution? We'll just check out from your repository. Does someone have a solution to this? Someone must have this. Let me, let's get someone's solution up here. Can I hear an account name? Can you spell it for me? B? Brad, there it is. Okay, great. And it's this one here. All right. So what Bradley did was he put everything in one function, in one file, which is okay. But normally we would split it up into files in a big project, obviously. Yeah. Okay. You're still working on it. Also, the class by convention. Usually, not everybody does this, but usually it's uppercase on the class name. And let's go ahead and is this running? Yeah. Oh, okay, great. So let's just look at it. So what we have is a class called WebList, and it has a private member variable called items. And this is what will store the items. And an item so we have a web page. It's just a list of strings. You know, hello, goodbye, I am not here, whatever. We just have a list of strings, and they're just listed on the web page. So the things that we want to list on the web page are stored in this vector of string called items. And when we create an instance of this class, the vector of string is empty. So the test code needs to call add item on it repeatedly. to pass in a new item. So every time we call add item, we're going to add the string into items. And then when we call print, that's when we're going to generate the web page. So add item is implemented here, and it's just a pushback. We just, whatever item is being passed in, we're going to add it to the list, to the vector of string. And then when we want to print, well, we've got to print all this HTML business. And this is the tag for an ordered list, so it's going to be a numbered list. And then we print the items in here, and then we print the closing tag to close off the ordered list, close off the body element, close off the HTML element. We're done. So the tricky part is here. Here we want to we need to iterate through. This is hard to read. Sorry. Tell me next time. Can't read that. So we need to, we're iterating. See, while I is less than items.size. Yeah, I would have used a for loop, but this is fine. This is great. You know, I would have used a for loop here, but this is great. We set I to 0. That's the first index. While the index is less than the number of objects in the vector, we output the item. Here it is, items of I. And we sandwich it between this HTML. And then we have to increment I. And we keep doing this until I is equal to size, the vector size. Then we're one past the last position. So we create an instance of web page, and we just call add item a bunch of times. And then we call print, and that's it. This is lab 8_3. There it is. And then if we want to generate the web page, you know, we'd do something like this. And there's our web page right there. And there it is. And you can open this up in the browser, and it'll show that in the list. All right, that's great. Brad, thank you very much for that. Okay, we'll see those who are coming in lab.